Hello everyone, this is section 9.4 class note problems on the pigeonhole principle. So question number 1 says, a small town has only 500 residents. Must there be two residents who has the same birthday? Let's identify the pigeon and pigeonholes and display the answer. Well, here we have the pigeons that are going to be the 500 residents, of course. And the pigeonholes Hello everyone, this is section 9.4 class note problems and the pigeonhole principle. So the first question has, a small town has only 500 residents. Must there be two residents that has the same birthday? Let's identify the pigeons and pigeonholes to explain the answer. Well, here clearly we have that the pigeons are going to be the residents and the pigeonhole are going to be the same of the year that we can do for birthday. So we're going to have 366. Let's assume that our normal 365 and maybe one of this year that has February 29. So we're going to go with 366. Now, notice that 500 is bigger than 366. And so by the pigeonhole principle, there is at least two people with the same birthday. And that is clear since if we have one person that fits every day, we're going to have 366 person for 366 day. We're going to have at least 100 more people that we can fit in that same day as somebody else. So at least we have two people with the same birthday, assuming that the rest of the 100 people have the same day of his birthday. We're going to have at least two people with the same birthday. Okay, so number 2. In a group of 677 people, must there be two who has the same first and last initials? There are 26 letters on the alphabet. Explain. Okay, so here, once again, the pigeons are going to be the 677 people, and the pigeonholes are going to be the initials, right? But we have 26 initials, and so because there's two first and last initials, we have 26 by 26. So for example, A and A or A and O as initials. So 26 by 26 is going to give me 676. That's close, but we still have that 677 is bigger than 676. And so by the pigeonhole principle, there is at least two people with the same initials. All right, so now question number 3. We have, suppose you have 5 integers chosen from T. So this is very similar to what we did in the slice. There must be 2 whose sum is 9. Just by identifying an appropriate partition of T into pairs. So notice that we have to get sum 9, we can have like 1 and 8. We can have 2 and 7. We can have 3 and 6, and we can have 4 and 5. And that's it. Those are the partitions that are going to give me sum 9. The pigeons are going to be these 5 chosen integers. And then the pigeonholes here are going to be the 4 pairs above. And so what happens is that by pigeonhole principle, if you pick 5 integers, because 5 is bigger than 4, you're going to have that 2 integers are going to lie in one of these bins. So you have that at least 2 numbers are going to be part of these bins. And so we're going to have at least 2 that add to 9. We have a pair that adds to 9. Okay. All right, moving on. Question number 4. In a group of 30 people, must at least 3 have been born on the same month. And so here we're going to use the generalized pigeonhole principle. We have the number of people is 30. And we want to kind of find the pigeonholes. The pigeonholes are going to be 12 because those are the months. But by the generalized pigeonhole principle, since we have that the ceiling of 30 divided by 12 is 2.5, which is ceiling to 2.5, which is 3, then we can consider k being equals 3. And so at least 3 people are born in the same month. Okay. So remember, by the pigeonhole principle, we can approximate using the floor of how many is going to be the amount of at least people that are going to hold the condition. Okay, so question number 5 says among 5 integers must at least 2 leave the same remainder when divided by 4. So, okay, so once again, the pigeons here are going to be the 5 integers, and the pigeonholes are going to be the 4 remainders modulo 4. So now, since 5 is bigger than 4, then by pigeonhole principle, we have that at least 2 integers have the same remainder. Okay? Remember that when we divide a number by 4, the remainder has to be less than 4. So we have 0 to 3 being the remainders possible. And so that's 4 types of possible remainders. But because we have 5 integers, then that means that if we're dividing those, the 2 are going to be having the same remainder. All right. So question 6. Among any n plus 1 integers from 1 to 2n, prove that there must be 2 that are consecutive. And so pretty much consecutive integers will be the pairs 1, 2, and then we can go with 3, 4, or we can go with 5, 6, so on and so forth until we get to 2n minus 1, 2n. And the pigeons here is n plus 1 integers that are chosen from here. And the pigeonholes are these n pairs. Pairs, not pairs. So these are the pigeonholes. And so because n plus 1 is bigger than n, then we're going to have that by pigeonhole principle. Then 2 integers are going to be in one of these pairs. At least 2 integers are allocated in one of these pairs. And so they're consecutive. Hence, consecutive. All right. Now, question number 7. Explain using the pigeonhole principle why the decimal expansion of 1 over 7, 0.142857 periodic must eventually repeat. What is the maximum possible period length for 1 over 7? Now, if you perform long division of 1 divided by 7 at each step, then by quotient remainder theorem, your residual, your remainder is one of the integers 1, 2, 3, 4, 5, 6. It cannot be 0 because otherwise it will be just it will be divisible by 7, and it's not divisible by 7, so that's why it gotta be one of these numbers, right? Um, and so that's not happening. So the pigeon here will be the remainders. Will be the remainders produce at steps. I don't know, like 1, 2, 3, so on. And the pigeonholes will be the 6 possible non-zero remainders. So here, with at most 6 plus 1, because I need that is bigger than the 6 possible. So with 6 plus 1 steps, a remainder must be repeated. By pigeonhole principle. Okay, so at the 7 plus 1, this is the pigeon, the number of pigeonholes. Sorry, at 6 plus 1 pigeons, right? Possible, which is the steps, right? Is going to be bigger than the number of pigeonholes. So at that point, we're going to start repeating the remainders. Okay, so once a remainder repeats, the digit pattern from that point onwards is going to repeat as well. So that's why the pigeonhole principle here occurred, and the maximum possible period is 6, or the maximum period length is 6. Okay, so when we see here 1, 4, 2, 8, 5, 7, we actually achieving that maximum in here. Right? All right, so those are all the examples of the pigeonhole principle.